This chapter of the Kitab will discuss about the Root Locus approach. But before that, we need to discuss stability. When designing any control system, stability is the most important criterion to be met. Stable systems give a finite or a predictable output. When the output produced tends to infinity, the system is said to be unstable. Unstable systems usually result in catastrophic events. Let's take the Tacoma Bridge fallacy as an example. In 1940, the Tacoma Narrows Bridge was built in US state of Washington. It was the third largest suspension bridge at the time. However, just 4 months after its construction, a strong wind blew across the bridge, causing it to flutter and eventually collapse. Let's analyze this bridge as a simple control system and see how it became unstable. Every system has a bunch of different parameters that defines it. For a bridge, there is length, the Young's modulus, damming ratio, and so on. Using these parameters, we form a mathematical model, which is a differential equation with respect to time. To make calculations easier, we find its Laplace transform and get the transfer function of the system. Solving this function, we obtain the roots, that is, the zeros and poles. In any transfer function, zeros are the values of s for which the output of a system becomes 0, thus obtained by equating the numerator of the transfer function to 0. Poles are the values of s for which the output of a system becomes infinite, thus obtained by equating the denominator of the transfer function to 0. We can plot the zeros and poles on the 2D S-plane that has the real and imaginary axis. This is a 3D plot involving the real, imaginary as well as system output axis. Since poles can make the system output tend to infinity unlike zeros, the stability of the bridge can be decided by the poles alone. If a pole comes on the left half of the S-plane, when translated into the time domain, we get an exponentially decaying output. Since the output is finite here, the system is stable. If the pole comes on the right half of the S-plane, we get an exponentially growing output in the time domain. Now this output is infinite, meaning the system is unstable. What happened with the bridge was that initially, when the wind was blowing, the bridge was able to withstand it, meaning it was stable with its poles being located on the left half of the S-plane. But with a much stronger wind, the poles shifted towards the right half, making the bridge unstable. Now this incident happened almost 80 years ago when the engineers had no way of predicting the system stability. Luckily, 8 years later, an American control engineer, Walter Evans, introduced the root locus technique. This is a graphical method for examining how the roots of a system change with variation of a certain system parameter. So, if wind speed was a parameter, we would come to know how the poles would move according to different wind speeds. And that is how we avoid catastrophe in engineering.